great pleasure for me to introduce Demitri. Demitri and I have worked together for several semesters now, and it may not sound that complimentary, but I thought the best way I could introduce his work was that it was actually useful. And to clarify what I mean by that, with a lot of these students, we love to see their development, we love to see their work as they go through the projects. But with the time that Demitri and I had to work together, he was able to move beyond that sort of expectation of simply working with what I had to offer in that sort of sense, that he finally got to a stage in the latter part of the project where he can actually begin to start to take a lead himself. And that is something that I think is quite rare and was very pleased to see in his development. So let's please have a warm welcome for my student, Demitri.
So I am Demitri Call, and my advisor was Dr. Tom Target, and what we worked on was characterizing size-mass relations of high redshift galaxies. By that I mean redshifts between a z-value of 3 and 4. And I'll explain the z-value just now, but this image here, what you see on the left-hand side, that gives you the kind of the Big Bang. This is going to be the evolution of the universe. So Big Bangs are on the left. On the right-hand side here is where you have, what we see today in the universe. And all across there is going to be, the evolution, what's happened in these 13.7 billion years since the Big Bang. And with that redshift we're looking at, redshift is a proxy for distance, it's a proxy for time. And so at these redshifts, what we're really looking at is we're looking at early galaxies. We're looking at galaxies that are about just under 12 billion years old. And so that is corresponding to a time right about here on the graph. And that's going to be at a time where it's peak star formation in the universe. And so that's kind of what we're looking at now. And why we're looking at this time is previous data from Fernando Buitrago. They did this data, this analysis of the same thing we're doing up to a redshift of z equals 3. So a little bit earlier than ours, and they were able to go to about 11.3 billion years ago. And as you see here, on the left-hand side of this graph, it's going to be a normalized size. So it's just going to be what we see over there, that top little point there, is going to be what we see today. It's going to be the size of all the galaxies that we see in our local area here. And as you go across the right, on the bottom, it's redshift value. So as I said, redshift is a proxy for distance and time. As you go in higher redshift, you're looking further back in time, at earlier times in the universe. And so as you see, as you look earlier in time, the trend here is showing that galaxies were a lot more compact. Up on the top trend line here is going to be disk-like objects. Those are going to be spiral galaxies, galaxies like our own here. And the ones underneath are spheroid-like objects, and those are going to be large elliptical galaxies. And as you can see, they really are getting a lot more compact at earlier times. And if you think about it, that can't continue. You can't have something be infinitely dense at some time where it's not going to be infinitely dense now. So we're wondering if that changes at the time we're looking. If it changes after, we don't know. So we're just looking because no one had done this before. And so the redshift value here, the z value I've been talking about, the way to get it is it's a simple equation. You take the observed wavelength of the light, you subtract it from the emitted wavelength. So an object is going to be emitting something, and if it's redshifted, it actually elongates it. It makes the wavelength appear longer when we actually look at it. So you subtract the emitted wavelength from the observed and then divide by the emitted wavelength to get your z value. And as I had said before, the z value they went to was z equals 3, which equates to about 11.3 gigayears or billion years ago. And we get an additional half a gigayear of look-back time. Now, what was keeping them from looking past that time before, why they could only go to a redshift of z equals 3, was something called the 4,000 Angstrom Break. Now, this break is something that's caused from dust and gas in the universe. So when there's dust and gas between us and these objects we're looking at, it'll obstruct some of the light. To get around that, we do things like look at longer wavelengths. For example, here, on our planet, we use radio waves because they travel through many things, and we can still hear them in our cars and pick them up wherever we are. Well, as you look at longer wavelengths in space, it'll get past and through more things as well. So you can look through this dust. What I have here is going to be a set of images here, all looking at the exact same point in the sky. And as you can, this little dip here is the 4,000 Angstrom Break. That actually represents about a 50% decrease in the flux we get, or the amount of light we receive from these objects. And so as you're looking at this point, you can't see much on the image, and you can't really get any data from it. And so I move on to the next filter. As you see, these little arrows here will denote where I am looking, what wavelength I'm looking at. You still can't really see much. As you're looking, you keep going longer wavelengths, and you're still not seeing any objects. You can't do any kind of analysis to these things here. And as soon as you actually cross past that, you can see the beginning of some object in the center. Once you cross past that break, you can all of a sudden see something. You're finally able to break through this dust and actually be able to take meaningful data. And so we push past this break, you get something even more clear here, and we're able to finally get data on these objects and push this correlation even further. And so the data we got, it's new data. It's from the Very Large Telescope in Chile. That's the actual name. I don't make these up. The K-band is what band we're looking at, and that's going to be a range of wavelengths that we look at, and it's centered on 2.2 microns. And so, normal visible light will be on the order of several hundred nanometers. This will be on the order of about 2,000 nanometers, so it's a little bit longer of a wavelength. And so that gets us to that z equals 4 value, gets us another 500 million years of look back time, we can look back and see how things have changed here. So what we do, we have all these images, we got this huge set of all these images and all this data, and we run it through this two-dimensional fitting algorithm. It's called GalFit. And what we do is we take all of the objects, all the galaxies, and we fit them to 7 different parameters. And the algorithm, the two-dimensional fitting algorithm, is called a fitting to least squares, or chi-squared value fitting. And so it's highly accurate, and we use it for the 7 different parameters, which the main one that we start with is always position. Just x, y, where is it on the screen? Where is it in the image, the object? And then the next one we have, we'll do the magnitude. The magnitude is just going to be how much light are we actually getting from this object. Take the area around it, count all the photons of light we're actually receiving from them, and that'll be the magnitude. Then we have the half-light radius. The half-light radius is not going to be the radius of the whole object, not going to be half of it. It's the radius in which half of the light is emitted. So if most of the stars and things are at the center of the galaxy, the half-light radius will be quite small, but if it's rather diffuse throughout the whole galaxy, it'll be a little bit larger. So that's different for each galaxy, and it helps kind of show how the distribution of matter is in each of these galaxies we look at. Then there's something called the Sursok Index. And the Sursok Index is a numerical representation of the light distribution. So it's how sharply it'll change the distribution of matter and light, as you go from the center of the galaxy. And then there's the Axial Ratio. The semi-minor axis is going to be represented by B, and the semi-major axis is going to be represented by A. So it's just going to be a ratio of how elliptical it is, how much it looks like an oval, not a circle. And then the last one has to do a lot with when you have very elliptical things, you have something called position angle, and that just tells you how much to rotate. If you have something here, you rotate it from the top, so that A is at a complete diagonal, it would be like a 45-degree position angle. It's just telling the algorithm how to turn this object so that it actually fits the data we have. And then the next thing is we have all these images, and any image could have a range from 1 to most I've seen is around 10 objects in it. And each blob of light here is going to be a different galaxy. So this one here, the object of focus for us will be the central object here, but there's 4 other objects on the screen. We have to fit to all of them. They all have to be fit separately. And so the idea is we take this image, we set up the files, and we run the algorithm through it, and the computer will make a model of these images. And what we want to do is take this raw image, the actual data, and subtract it from our model. When we do that, we want to see just uniform noise. So by noise, I mean this background here, we want the whole screen to look like that. That would be a strong indication that we have a good fit. So for this actual image, the computer model ends up looking like this. And when we get back to the initial image, what we're going to do is just subtract the two. So take this image, subtract the one I just showed you, and what happens is we end up with a rather uniform background, which is great. That's a strong indication that what we have is usable material, but it's not all we can go on. We can't trust everything right then and there, so we have to go through something called reliability testing or convergence testing. And with that, a good example is the chi-squared value, or the fitting least squares. A lower chi-squared value, so anything at the little trough down here at the bottom, will be represented. It'll make us more reliable, our data will be more robust if we're hitting those lower values of the chi-squared. And at the bottom axis, you can use any starting point. So for example, the Sursok Index I mentioned, which is the numerical representation of the light distribution, you can use that, and as it goes, it'd just be different starting points. So if I were to use Sursok Index as an example, I could start with a Sursok Index of say 1. A Sursok Index of 1 is a good representation of a disk-like galaxy, again, like our own, like the Milky Way. And we start it here, we run the algorithm, and we can end up with it over here, and that's great. But that's only one point. We don't know at all if that's going to be reliable, if we can use that in our final data set. So we have to start it from a series of points, a series of different things. This would be like starting from a value 2, rerun it through, and you end up in the same spot. Fantastic. But you can keep trying further points away, and what happens is you might start here. You don't want it to get stuck in a local minimum. You want it to make sure you're finding the global minimum of this graph or of the object that you're going to be fitting. And so you'd want it to not get stuck there, but end up in the actual point. And when you have a bunch of them ending in the same results, that's a strong indication that you have usable data. However, you can have things, outliers, or if you start way far from the actual value, you can have it get stuck. It just can't get over this hump here. It's too difficult. So when you do that, if you have 3 or 4 other good points that all go to the same result, and you end up with having the same result in good looking image when you visually see the background, then you can be really confident that you still have a usable image. And so to show what a good image is and a good and a bad one, I have a good fit here. So this is going to be representing the different parameters, position, magnitude, half-light, so on. And then over here, it's a little bit difficult to read, but here you have the same things with the actual starting parameters here, what actual values I used to start each iteration. And underneath them, you have the values after the algorithm ran through. So the easiest way to look at this, if you look at the half-life radius, they're all 5.03. They're highly consistent, no matter where I started from. For example, I started this one with 1, started this one from 5, started another one from 3. They all end up with the same result. That's great. Sursok Index, same as well, 0.99. It's going to be a very disk-like galaxy, and it's going to be highly consistent through all the different iterations. You can have ones that don't look so good. This one would be one we would keep in our data set and be making to our final correlation, but other ones like this won't be the same. This is a different image, but run through the same process, run through the same convergence testing, and you have things where the half-life radius will hit these little star means we set a wall. To go below a 0.5 is non-physical, it doesn't make much sense. And so we tell the algorithm to just stop. But what happens is, we have ones down there at 0.5, we have another one at 1.08, factor of 2 off, and it gets worse when you look at the Sursok Index. You have ones at 1.83, you have ones at 5.36 or 5.75. It's not very consistent, and it's not something we could use in our final data set. So anything like that, we have to get rid of our entire set. And we ended up with about 40 images after all of this convergence testing to use in our final correlation. And what we found was that the disk-like objects here, this is again the same graph that I'd shown at the beginning for our motivation. I only added this part here and continued their trend line. The disk-like galaxies here follow spot on with what was shown to be the trend from before, but the spheroid-like galaxies or elliptical galaxies, they are a little bit above that trend line. They're kind of suggesting that there might be a tapering off, which would make sense. They can't get infinitely dense, they have to do something. It would have to either get less dense or taper off and flatten out. And it does make sense that we would see this in the spheroid-like galaxies first. Spheroid galaxies or elliptical galaxies are in a higher evolutionary state than the disk-like galaxies. So we would see those that change arising in these galaxies first. But in order to confirm this, we'll need to have another data set with new data at longer wavelengths so we can look a little bit past this barrier we've reached here. And beyond that, I would like to thank Dr. Tom Target for all of his help, thank the Department of Physics and Astronomy, and then my collaborations, definitely want to thank Mom Gill. She was starting it when I got into this and helped me quite a bit as I was learning to do this research. And I want to thank my family for being there the whole time.